Carla's back? You're good. Yeah, you're good. I came out to get you, but. All right. So here's the rest of this chapter. Really. We are going to do section 4.7, okay, and that will take us several days. Okay. Section 4.7 is all word problems. I know. Just what you guys wanted to hear. Optimist word. Tons of word problems. Optimization. Yeah. And then we do section 4.8. Way too late. And then we take our test. No, I love this. This section is like one of my favorites.
Every section is one of your favorites.
This is one of my favorite sections. I love section 4.7. I'm really not. I think that it's really fun. My version of fun, but I'm a big nerd. Okay, so where are we headed? Well, we're going to do section 4.7. That will take us, what is today? Wednesday? It's really kind of like a Thursday, though, right? Yeah. That'll take us today and tomorrow through the end of this week. And then I do want to leave one or two problems on Tuesday. At least one problem on Tuesday for when we get back. Because I don't want it to be like completely lost in our brains after the 4-day weekend. Okay? So we're going to do notes today and tomorrow. I want to leave one or two problems till Tuesday. And then I want to quiz over just section 4.7 by the end of next week. Okay? I want to quiz over just section 4.7 by the end of next week. I'll teach you 4.8. 4.8 is like a 1-day real quick lesson. Not much to do there. And then we will test over sections 4.5 through 4.8. That'll be the second test for the 9 weeks. And that will be it for the second 9 weeks. Excuse me, third 9 weeks. Okay, that will be it. That 4.5 to 4.8 test will be the last grade for the third 9 weeks. And then it's the home stretch, right? Right now, I have that test, that 2-day test, scheduled to be on the Thursday, Friday of the week before the end of the third 9 weeks. Okay, so we will actually have to. We'll start into like chapter 5, that last week of the third 9 weeks. But I'm not going to put any grades in until like the fourth 9 weeks. Okay. So that's where we're headed. We're going to do section 4.7, several days on section 4.7. I want to give you a bunch of time to work in class. I want to work through problems. I want to look at homework problems together. This one is really one where you're going to need to think outside the box a little bit. Okay? All right. Optimization problems. Remember the related rates problems? This is very similar to that. Ones where you have to take a situation, look at how we could model it with an equation, and use calculus to find. Now, in the related rates section, my end result was always like, okay, how fast is the balloon increasing in size? Or like, how fast is the water draining from the tank? How fast is something growing? How slow is something growing? Whatever it may be. It was looking at the rate of increase or decrease. Okay? That's what we were looking at. We were looking at the rate of increase or decrease. So basically, we were looking at the slope of the tangent line. We were looking at the derivative at that time period, at that instantaneous time. But what we've learned since that point is that the derivative is not just useful for slope of the tangent line. It will also actually tell you, we can also find out when the slope of the tangent line would be 0, when we would have a maximum or minimum value, when we could optimize a situation. And what do I mean by that? Optimize means I could take the biggest or smallest possible amount. The biggest or smallest possible amount. I will tell you that, like the AP test, for the AP Calc test, I mean, there's a bunch of optimization problems. Like, this is very applicable stuff. Okay? We are just going to scratch the surface a little bit, and it's going to take us several days. Like this is a lot of their AP test. Okay, those like extended response problems that they have. I mean, it's like A, B, C, D, E of optimization problems. Okay, for us, we're really just going to kind of scratch the surface and see, how we can use calculus to find maximum or minimum values of something. The methods that we've learned in this chapter for finding extreme values have very practical applications in many, many areas of life. As a business person wants to minimize cost, maximize profits. A traveler wants to minimize transportation time. Fermat's principle in optics states that the light follows the path that takes the least time, the minimum amount of time. In this section, we solve problems as maximizing areas, volumes, profits, minimizing distance, times, costs. That's what we mean optimize. The word optimize just basically means to find those extreme amounts. Find the biggest possible or the smallest possible, whatever our problem lends itself to. In solving such practical applications, the biggest challenge is often converting the word problem into mathematical optimization, right? That's the issue. And I think you guys would agree with me. Finding the derivative and finding critical points, I mean, we've done that for a long time now. The issue is going to come, how do I create the equation that will allow me to find the critical points, that will allow me to find the maximum and minimum values? That's going to be our issue, okay? Now, this was back way long ago. We kind of talked about this, but I'm going to run through these things because this is what goes on in my brain, right? Now, I'm not going to like follow this to a T for every time, and this isn't something that you necessarily need to like write down and say like, ooh, here's step one, here's step two. No. But this is a good method of thinking. First thing, really thoroughly understand the problem. Read through it several times, 3 or 4 times if you need to. Think through, try to visualize if need be. Understand the problem. The first step is to read the problem carefully until it's clearly understood, several times if you need to. Ask yourself, what do I know and what do I not know? What is known, what is unknown? What are the given quantities and what do I have to find? And what are the conditions? Basically, what are the constraints of this issue? What's going on here? Second thing is, once you clearly understand the problem, try to draw a diagram. I will tell you right now, for every single one of these problems, I draw out a diagram and label the diagram with the given pieces. In most problems, it is useful to draw a diagram and identify the given and required quantities within the diagram. That will help you to visualize what's going on. Okay, so after we've understood the problem, draw in our diagram. Then what we're going to do is introduce notation. We're going to assign variables and assign quantities. What is f of x? What is y? What is x? What is dy dx? What is our derivative? What are those things? And what do they represent? Assign a symbol to the quantity that is to be maximized or minimized. They call it Q for a lot of times. Also select symbols A, B, C, X, Y for other unknown quantities and label the diagram with those symbols as well. I think this is a funny statement. It may help to use initials as suggestive symbols. For example, A for area, H for height. It's like, okay, come on now. This is a calculus book, not like an algebra book. Number 4, express the quantity, the Q, in terms of some other symbols from step 3. And this is going to be extremely important. That is a deceivingly small step, okay? That's going to be a huge task right there. To find the function that we're trying to minimize or maximize, and then express it within one variable, right? Get it so there's just one variable within our function that we're trying to maximize or minimize. Like only x's, only y's, only t's, only r's, whatever it may be. Get the function that you're trying to maximize or minimize whittled down so that we only have one variable within that function. Because if you try to differentiate with more than one variable, well, then you're looking at implicit differentiation, and you don't even want to go there. Okay. Next step. If Q has been expressed as a function of more than one variable in step 4, use the given information to find relationships. Okay, that kind of like ties that in. Important piece here to step 5, though, write the domain of this function in the given context. Because more often than not, if it has a context, then there's going to be a domain, a reasonable domain. Like if I'm talking about time, I can't have negative time. If I'm talking about a quantity, like a physical quantity, can I go into negatives? Because sometimes you can. Like you can go into debt, you can go down into negative money. Like you have to think about reasonable quantities, reasonable domain. Then use the methods of section 4.1 to 4.3, what we've just learned, to find absolute maximums or minimum values of that function. In particular, state the domain of f as a closed interval. And then we will use our good friend, the closed interval method. Okay, this is what we learned, I think it was back in section 4.1 or 4.2, the closed interval method. What is that? That's that thing with the table where we take the endpoints and any critical points in between and find the maximum or minimum value of the function based on all the y values of those critical points and the endpoints. Because if we're looking at the closed interval, which in most cases we are for these optimization problems, what you're going to be looking at is, okay, I've got my endpoints and my critical points as the only possibilities for absolute maximums and minimums. Sometimes it will be an endpoint. Sometimes to maximize something, it will be all of something and none of the other. Okay? That is the case, that can be the case. All right. Shall we get into it? Excited. All right. Our first problem here. A farmer has 2,400 feet of fencing, wants to fence off a rectangular field that borders a river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Let me read that again. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field. And it borders a river, and we are going to assume that river is straight, not curved. He needs no fence along the river. Hi, Gio. Oh, sorry about the interruption. That's okay. See you, Gio. He needs no fence along that river. What we're going to find is what are the dimensions of the field that has the largest area. Okay, so first thing that I'm going to do here is I always like to write out what am I trying to maximize or minimize? What am I trying to optimize in this case? So I wanted to find, do I want to maximize or minimize, and what do I want to do with it? Or what am I trying to, which value am I trying to maximize or minimize? So what am I trying to do here? What's the goal? What's the goal? Maximize area. Maximize area. So I'm going to write that out. I'm going to clearly define for myself. I want to maximize area. Right. I always like to make that statement right at the beginning because now what am I going to be doing? I need to create a function for area so that I want to find the derivative of the area function. Okay, now let's draw a picture. Okay, I've got a river. Okay. Just the waves, and then I've got this rectangular fence, this rectangular field, whatever you want to call it. Let's make variables for our length and width. Okay, let's call this x and this y. Notice again that we are assuming that we don't want any fencing along that river. We don't want any fencing along that river. Okay, what is the area of this rectangle? X times y, right? Okay, what else do we know? What else do we know?
X and y has to equal 2,400 if you add them together.
Okay, I have 2,400 feet of fencing, right? But be careful, it's not x plus y equals 2,400, is it? What is it? Not x times y. 2x plus y. Right? Because I've got x plus y has to equal 2,400. almost like the perimeter, but I'm leaving off one side. Now, one of the hard things here I said was, okay, we want to maximize area. We want to optimize the area function, right? Which means we're going to find the derivative of the area function. I need my area function to only include one variable. Well, what's the easiest variable to solve for, x or y, in this equation that we came up with? Y, right? So y is equal to 2400 minus 2x, right? Right? What I'm going to do is replace y in that area function. Area is going to be equal to x times 2400 minus 2x. Let's reduce it a little bit. I don't want to do any sort of product rule when I find a prime. So a is equal to 2400 x minus 2x squared. What's up, boy? Freshman talking all gangster. You got something to say my face, boy. All right. All right, let's take a look here. So I want to maximize area, right? So that means I want to find the derivative of the area function. So a prime is going to be equal to, well, 2400 minus 4x. Now, the only possibilities of a maximum or minimum value within that function occur at the critical points, right? So that means I've got to find the zeros of that function. 0 is equal to 2400 minus 4x. Okay, add the 4x over to the other side. Divide by 4, 600. When x is 600. When x is 600. Okay, you know what we haven't done yet? Talked about our domain. What's the smallest possible x value I could have? 0. Right? I could have 0. And I guess we should talk about this as a bracket because it's the closed interval method. And then what's the biggest possible x value I could have? What's the biggest possible x value? If I used all of my fencing for my x values, what would be my biggest possible x value I could have? Not 600. 1200. 1200. Why? Because I use all of my fencing for just those two sides. I mean, that would like enclose nothing though. You know, you just have like a fence and a fence. So we got 0 to 1200. Does our maximum / minimum point fit in there? Yes. So we have the closed interval method. 0, 600, 1200. Now, I think, we could logically throw out 0 and 1200, but it's good to just, go through the motions, right? Just so we know, okay, yeah, we're going to be looking at both endpoints because both endpoints could have a possibility of being the maximum or minimum value. Oh, no minimum. I only care about maximum. All right, so if I plug in 0, now what am I plugging 0 into? What am I plugging 0 into? Not the derivative, the area. The area. The area function, not a prime, but area. 2400x minus 2x squared. Right, that's what it's going into. Because I want to find which x value gets me the biggest area. Right? That's the goal. Which x value gets me the biggest area? Well, obviously, if I plug in 0 here, my area is going to be 0. If I plug in 1200, I'm going to jump to 1200. If I plug in 1200, what's going to be my area? Well, spoiler alert, it's 0. If I plug in 600, I get 2400 times 600 minus 2 times 600 squared. Oh, shoot. I missed a parenthesis. Stop it. Oh, geez. 2400 times 600. Right here. Insert a parenthesis. 2400 times 600 minus 2 times 600 squared. 720,000. So obviously my 600 is the winner, right? Obviously this gets me the biggest amount of area I could possibly have. Now, what did it really ask me though? What are the dimensions, right? What are the dimensions? So the x value is 600. So it's 600 feet by what? Well, what's my y value then? Oh, I have an equation to find my y value given my x value. It's 2400 minus 2 times 600, or 1200. Oh, come on. 240,000, excuse me, 2400 minus 2 times 600. It's just 1200. Why am I doing this? Just 1200. 600 by 1200. Those are the dimensions. That gets me the biggest possible area. Are there other options for a rectangle? Of course. Do 500, 500, 1400. But is that the biggest area? No. Biggest area is 600 by 1200. Okay, that was a relatively simple one, where the area equation was a very simple one, x times y. And we were basically given almost like the perimeter to plug into. Let's try another one. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize cost of the metal to manufacture the can. I mean, how more real life applicable could you get? You're in a company, you're trying to minimize costs, right? You're trying to minimize costs. I know I have to hold 1 liter of oil. 1 liter. If I want to minimize costs, I guess let me ask this question. If I want to truly minimize cost, what else has to be minimized? Size, right? But am I talking about volume? No, volume's stuck. Right? Volume is stuck. And actually, the book assumes that you know this, that 1 liter is actually equal to 1,000 cubic centimeters. Right? The book assumes you know that conversion. It's funny, when I started doing the notes last year, because obviously, again, last year was the first year I taught this, I always like to do the problems without trying to look at the book for the answer. And I was stuck, and I was like, I can't figure out how they, I've got liters, I've got centimeters. And they were like, assuming that 1 liter is 1,000 cubic centimeters. Like, oh, for real? So it assumes that you know that. 1 liter is 1,000 cubic centimeters. But we're not trying to minimize area. We're not trying to minimize volume, right? Volume is stuck. I've got 1 liter, and I'm not trying to get any smaller than that or bigger than that. I want it to hold 1 liter. So what am I trying to minimize then? If I want to minimize costs. The size in terms of what? We whispered it over here. Area. And what do we call area in terms of a 3-dimensional? Surface area. So I'm trying to minimize. So to minimize costs, we will have to minimize surface area. Okay? So I've made my statement about what I want to minimize or maximize. I'm choosing to minimize surface area. Let's draw out our picture. Okay, we've got a cylindrical can. We know we want it to hold 1 liter, and we want to find the dimensions of that can. Now, dimensions in terms of, I need my radius and my height, right? Because that's what our surface area is defined on. I want to minimize surface area, so I need to know what the radius and height would be. You know, how big the base of the can and how tall the can would need to be to minimize costs. So let's call my radius R and my height H. So that would mean my surface area formula is this. Surface area of a cylinder. Okay, remember surface area is 2 times the base times the height. 2 times the base plus the height, excuse me. 2 times area of the base. Well, the base is a circle, so it's 2 times pi r squared, right? 2 of the bases, and then the distance around. Well, it's the radius, it's the circumference of the circle times the height, plus 2 pi r h. That's the surface area formula of a cylinder. 2 pi r squared, the area of the bases, top and bottom, plus the area around the outside. 2 pi r, that's the base, the linear base around the outside, times its height. 2 pi r squared times 2 pi r h. Now, what we have not looked at yet is volume, right? I have not used that whole volume piece of it yet. So let's use the volume formula. Well, the volume formula is equal to pi r squared, the area of the base, times the height, right? The area of the base times the height. I know what my volume needs to be. My volume, again, was stuck. Pi r squared times height has to be equal to 1,000 cubic centimeters. Okay, well, what's the easier variable to solve for here? H or R? H, by a long shot. I don't want to have to go plugging in any square roots. No, thank you. So let's divide over by pi r squared. So that means 1,000 divided by pi r squared is equal to my height. So I've got now an equation that I can use to plug in for my height. So let's go back to my surface area. Surface area is 2 pi r squared, okay, no height there, plus 2 pi r times my height, which is 1,000 divided by pi r squared. The volume divided by the area of the base. Let's reduce. So my surface area is 2 pi r squared. Now watch what we can do here. I can cancel out the pi, and then the r with the one of the powers of my denominator, right? So this is essentially going to be plus 2,000 over r. Because it would have been like 2,000 pi r over pi r squared. So just reducing that out before I multiply it. Now, at this point, I'm reduced as I can get. So now I need to optimize surface area. I'm going to need to minimize surface area, which means I need to find the derivative. I want to find surface area prime, basically. Now, do I need to do any sort of product rule here? Be careful. I don't need to do any product rule here. A lot of people might think, oh, I got to do product rule because I see, oh, no. Pi is a number, right? It's like 6.28 because it's 2 pi. I really want to find the derivative in respect to r. So this is, bring it out front, 4 pi r plus, now I need to find the derivative here. Now, if r is in the denominator, isn't that r to the negative first power? So this is really 2,000 r to the negative first. And I'm going to write it like that. We did this a long time ago when we were finding derivatives, where we rewrote problems where the variable was in the denominator with a negative exponent because it makes our life easier because it's technically polynomial at this point. So this is now a negative 2,000 r to the negative second power. Right? Bring the negative 1 out front, make it negative 2,000, drop it down in value 1 to the negative second power now. That's the function I want to find the zeros of. Because the zeros of the derivative tells me where my maximum or minimum points would be. So 0 is equal to 4 pi r minus 2,000 r to the negative second power. All right, let's add over the 2,000 r to the negative second is equal to 4 pi r. And just adding it over to the other side. And let's turn that back into r to the, well, I guess we could do it this way. We divide by r to the negative second power. So that's easier. 4 pi, because what's my power on r now? R to the first over r to the negative second. Add it, or subtract exponents. 1 minus a negative 2 would be r to the third. Okay, divide over the 4 pi. This is going to be a decimal now. 2,000 divided by 4 pi is, you know what? I should have put that in parentheses. 2,000 divided by, I don't know if that would matter here. Pi is weird. It did matter. 159.15. 159.15. And that's equal to r cubed. And then we cube root that. Cube root. And I get 5.42. 5.42 as my radius. Okay, now, I said all along, okay, so that's my only possibility of minimizing, right? It's my only possibility of minimizing. Why is that my only possibility of minimizing? Well, I've got to think about it this way. What's my smallest value that r could be? Like if I were to think about my domain, what's my smallest value r could be? 0, right? What's my biggest value r could be? There's really no restriction, is there? The only restriction I have is that it's got to stay under 1 liter, right? It's got to stay under 1 liter. And obviously, if I make my radius bigger and bigger and bigger and bigger and bigger, is it going to stay under 1 liter? No. So my domain is really 0 to infinity, okay? Do I have the closed interval method here? I don't. But what I can say is this. If I make this number line and I look at 5.42, right, I'm going to get a negative and a positive on either side. Spoiler alert, you can just pick numbers if you want to and see what happens. But I'm going to get a negative then a positive. And guess what that means? That means that it's going to decrease, then increase, right? That's going to decrease, then increase, which means this is definitively a minimum value. And if this keeps increasing, am I going to have, and there's no possibility of having another extreme value because this is the only one we could possibly have, because it's the only 0 that derivative and there are no other places where it like doesn't exist or anything like that. Because it's going to keep going up and up and up and up and up and up and up, is there any possibility of it turning back down again and getting another minimum value? No. So this is the only possible minimum value that I could have. Now, all of that to say, bingo, there's my winner. 5.42 is my radius that will have the smallest surface area. Now, understand it. We're not done yet because it wanted the full dimensions. We wanted 5.42 centimeters as my radius. But we also need to define what my height is. Well, lucky for us, we had an equation. Height is 1,000 divided by pi r squared. Height is 1,000 divided by pi r squared. Well, radius is 5.42. So 1,000 divided by pi times 5.42 squared. 10.84. So you tell me you want a can of 1 liter. I say the cheapest can is going to have those dimensions. The cheapest can is going to have those dimensions. I think that's a pretty worthwhile thing to do. I mean, like, yeah, there are a lot of different applications I could tell you, but man, that's pretty good. All right, we'll stop there and we'll pick up there tomorrow. Sound good?